Hello and welcome to Varsity Eco. Today we are going to start classical demand theory and in bracket ordinal utility. That means we are going to study classical demand theory obviously, but under the structure of ordinal utility. Now if you have gone through the last class, then you know that utility theory and demand theory are different, and that is why we mentioned specifically that today to construct this demand theory, the utility that we are going to use will be ordinal utility. Okay, now first the important background. The classical demand theory uses a preference based approach to express the objectives of a decision maker. That means the preference will provide the identity. The preferences of a consumer is summarized by a preference relation. So who is the consumer? The consumer is that individual who has such and such preference relation. So where does ordinal utility comes into the picture? From this preference relation we will go to a utility function later, and while considering or defining that utility function, we will define it such a way so that we end up allowing only ordinal utility, but more of that later. Okay. Now, this setup is the longest topic of microeconomics. If you take any good book, starting from Mas-Colell to SRC to Snyder, at least 3 chapters has been dedicated on this simple topic of classical demand theory. Okay. Now, the backbone or the framework are the axioms, which are the central topic of today's class. And different books I've seen at times comes with different set of axioms which are necessary to make. I will follow Mas-Colell, which we call the Bible of microeconomics, so that we do not first of all take extra axioms, and secondly we do not club axioms in a way so that one of them become redundant or unnecessary or implied by other set of axioms. Because when you are making a structure based on axioms, there is a certain rule of making them. Okay. Now, in UG1, I understand that this approach will be more or less unknown to you. But if you open, let's say, Theory of Games and Economic Behavior by John von Neumann, there you will see a nice explanation written by Neumann while he was constructing the axioms for the theory, how and why the set of axioms that he had chosen there is the proper set of axioms. Okay, more on that later. The second important point is that Mas-Colell is definitely a postgraduate standard book. So if you open that book, you will see that the structure is based on N commodities, which is the general structure obviously. Now N commodities is obviously beyond the syllabus of UG. So how are we going to handle this class? I am going to reduce the structure to 2 commodities, which is in the syllabus of UG, and we will handle it that way. So the notations, the structures that we are going to write, all will be following Mas-Colell, but within a structure of two commodities, so that we learn the correct thing in the correct language, and again we limit ourselves within the syllabus that we have. Okay, and classical demand theory is not only a topic which is important by itself, okay, it's important for those who will be sitting for entrance in future, and also it is important for the next chapters of production and cost that we will do after this, primarily because the structure of production and cost and the structure of consumer behavior, in the mathematical sense, they are quite similar. Okay, so our journey will be something like this. We will start with axioms, that is today's class, and it's a long topic, so we will also take the whole topic in parts. So we'll go from axioms, we'll go to some theorems, which will also be taught in today's class. Then the diagrams of IC, because I have seen that most of the students get confused about the shape of ICs under different preferences. Okay, and then the mathematical exercise of optimization, where the techniques varies according to the ICs. And then obviously the last topic is duality, which is also quite difficult, definitely, but belongs to this topic, and which will also give us a glimpse of how it looks under production cost. Okay, so let us start now. So now we will be looking at the axioms, obviously, but I'll just request you to keep pen and paper and possibly write down what I am writing on the whiteboard, because the language here is of vital importance. If you write something else, then it will mean something completely different. So let's just say that it's nearly not allowed to write in your own words, and obviously it's a highly mathematical structure, but this is indeed the true structure behind all these clothings, foods and other things that you read in an UG book. Okay, consider a two commodity world denoted by good 1 and good 2. Okay. Under preference based approach, the objective of the consumer is summarized, as we said earlier also, in a preference relation denoted by R. So this R is actually what we generally see in undergraduate book. Remember, this is a preference relation in economics, but because it's a relation, so to say, it's the exact same idea of mathematical relation that you will find if you go through any book of modern algebra and study set relation mapping. So preference relation is just that kind of a relation. Okay, so denoted by R, or sometimes it is also denoted by this symbol. I have seen this obviously either in maths book or once I have seen it in, I think, Delhi school question also, but now it has become CUET. So anyways, just know it if you are sitting in future for entrance. Alright, and just a word of caution, this R is our relation and this R is real line, because in this structure we are going to use both of them, okay, and so don't get confused. Alright, consider a consumption set of alternatives or set of, this is more familiar to you, so set of consumption bundles X. So this is the set with members small x, which is obviously a vector x1 comma x2, right? Two commodities 1, 2. X basically denotes the quantity, and then we can, if we write y, so it will mean y1 comma y2. If we write z, then it will mean z1 comma z2, etc. Okay, so this is the notational structure. And remember, these are first brackets, right? So this is a, mathematically speaking, this is an ordered set. This is not just a simple set, like unordered set, right? This is not this, right? So at the same point, we are also referring to a point in a two-dimensional space. All right. Okay. So now our definition of preference relation. Remember, if somebody asks you, or if you wish to write, you have to write the exact same things when it comes to definition, right? All right. Preference relation is a binary relation. That means you need at least two. So binary relation on the consumption set X denoted by R or this symbol, okay, defined as X or Y implies and implied by X is at least as good as Y, where obviously, as we said, X is x1 comma x2, Y is y1 comma y2, and this X belongs to R2. At UG level also we can write plus. That basically means we are not going to consider, actually we should give a union to with 0 also. Technically we also take, if you are consuming nothing, like that happens with the quasi-linear utility function. Okay, but we are definitely not going to allow negative quantities at this level. Okay. All right. And in MSc, obviously, in PG, this also changes. Anyways, now we can derive two other relations from this R on X. One is the strict preference relation, and the other one is the indifference relation. Okay. two relations derived from. Number one, the strict preference relation P. The strict preference relation denoted by P is defined by XPY implied by XRY but not YRX. So this is a negation, right? I think in some UG book you will also find not written here in English. And read as X is strictly preferred to Y. The primary reason that we are studying this in detail, because I have seen in the last 8 years many students having many different sentences except the correct ones, which leads to many ideas except the correct ones. Okay. Number two, the indifference relation. I. So again, the indifference relation denoted by I is defined by XIY implied by XRY and YRX, and read as X is indifferent to Y. Now, in the last class of cardinal utility theory, I have talked about rationality and how the meaning was not really definite in the initial days of microeconomics. But here we have a very clear definition of rationality. So do not keep in your head some other meaning of being logical or thoughtful or something like that. There is a definition, we are going to write it, and it is what we mean by the term rational. Okay? So definition of a rational preference relation. Rational preference relation. The preference relation R is rational if it possesses the following two properties. Number one, completeness. What is it? For all x comma y belongs to capital X, either x are y or y are x or both. What it essentially means is that given a consumption basket and given any two elements from it, you cannot say I don't know. You have to say something. Then transitivity. For this we need three elements. So for all x, y, z belongs to X, if x are y and y are z, then x are z. This theoretically actually assumes, in real terms, it assumes two things. Number one is the role of it. It's basically, transitivity is a consistency criteria, you can say. Okay, your behavior is not inconsistent. Sometimes you say I prefer this over x over y, and you say I prefer y over z, and then suddenly you say no, I prefer z over x. So that's the inconsistency that we are trying to rule out here. Okay, and the other thing is, if you go by the size of the domain, actually, is that you have a very good memory. Okay, because in real world, what happens is that when you go through 6, 7, 8, 9 or more than that number of choices, you simply forget the first two. Or note 1. Observe that, this is important, completeness can be used to derive the strict preference and indifference relation on X. That is the two that we derived already. Okay. And note 2, this is why I said at the very beginning that I have seen many books coming with many different set of axioms. Okay, but they are not needed all the time. So this is, as I said, the correct set of axioms in the correct order with the correct language. Okay. In some books, the axiom of reflexivity is added in this list, but reflexivity is implied by completeness and therefore redundant. Okay. So now we are going to write a theorem with 3 results which will actually settle this debate. I am going to prove only one of them. The other 2 are actually easy. So the theorem. If R is rational, then number 1, P is both irreflexive, which means XPX never holds, and transitive. Number 2, I, that is indifference relation. I is reflexive, transitive, and symmetric, which basically means that I is an equivalence relation, right? So an equivalence relation. Again, I will say as a background, you just open a book of algebra, modern algebra, and just read set relation mapping. Okay. And number 3, if X, P, Y are Z, then X, P, Z. That means that to apply transitivity, because here that's what we are doing. Okay, to apply transitivity, I must have P here. But even if I do not have P here, I can prove as long as R is rational, this P and R will lead to P. Okay, so we are going to prove the third one. The other two are actually pretty simple. You can do it on your own. All right, and if there is a problem, you can just let me know in the comment box. Okay. So 3, proof. So R is rational, and because R is rational, it is complete and transitive. So by completeness, either Y are Z or Z are Y or both. So case 1, if both, then YIZ, and XPYIZ implies XPZ. Because I at some level means basically you can substitute. I mean, in a very crude sense, we can say that. It's true. So if both of them are not true, so then Y are Z, but not Z are Y. Okay? Which again implies that YPZ. And then by transitivity, XPYPZ implies XPZ. Okay. Now, this mathematical structure is pretty strict and contained, but before ending this section and before going to utility function and other assumptions, let me just say that there is something that we never said here, and an angle which psychology brings into the picture of economics today is that the choices matters obviously, but the way these choices are presented to you, that presentation also matters. That's called framing effect, how the choices are being presented to you. When you open OTTs like Netflix or Amazon Prime, you have been given a lot of choices, but remember there is a very specific presentation, and that presentation varies from person to person, because presentation can guide choices. Okay, so in the next section we'll start with utility function. Okay, so let us now start with the definition of a utility function. Before that, I must say that our claim that the consumer is summarized by a preference relation is there, and theoretically the knowledge of the preference relation is sufficient, but still we use utility function to kind of reduce our task. Alright, a function U maps from X to R, the consumption basket set, is a utility function representing preference relation R if X or Y implies and implied by U of X greater than equal to U of Y for all X comma Y belongs to capital X. Now, some important things. Utility function that represents a preference relation is not unique. That's why the article A is being used and not the. And 2 is that any strictly increasing function H, which maps from R to R, Hx equal to f of u of x such that f dash is positive represents the same preference or preferences as u dot. Okay, and this is important because this happens as we are interested in ordinal utility. Okay, and in the last class, in the end of it, I have discussed that our view towards this ordinality and cardinality is very simple. If you take a function and if you go through the strictly increasing transformation that we have written, the properties that change, they are called the cardinal properties, and the properties that do not change are the ordinal properties. And because here we are interested in ordinal utility, we are saying that it represents the same preferences. Okay? Our theorem. A preference relation R can be represented by a utility function only if it is rational. So here you have the role of rationality. Okay. So now we will move into two sets of assumptions which are vital, because our objective is to end up with an IC which we call the usual IC, that is convex to the origin. Okay. So for them we will take two kinds of assumptions. The first one is called desirability assumptions, which means that we desire. It's not that they're really needed or something, but if they are there, then it's all the more good. And the second is the convexity assumptions. That is to make the IC convex to the origin. Okay. So in the next section, we'll just write them down and we will end the class with a definition of IC, or indifference curve, both in a mathematical sense, also the way we usually write it in economics. So now we are going to start with the desirability assumptions. This desirability is a term taken from Mas-Colell, obviously. What it means is that we can make do without them, but it's better if we keep them. Okay, so we desire them to be true. Anyways, so here we are going to deal with monotone, or at times what you read monotonic, and local non-satiety or local non-satiation. In very simple word, which is also known as more is better. Here we will look at their proper definition. So, definition of monotone preference relation. The preference relation R on X is monotone if small x belongs to capital X and y, this is double greater 2 strictly greater than sign, okay, and this is for vector. I'm going to say what it means. Okay, so y double greater x implies ypx. It is strongly monotone if y greater than equal to x and y not equal to x implies ypx. So this sign basically means that in a two commodity world, these signs are actually in general they are given. Anyways, so in two commodity world, what it means is that y is y1 comma y2 and x is x1 comma x2, that we know. Now, how can it work? It can be that y1 is strictly greater than x1 and y2 is strictly greater than x2. So this is the case here. Now, if y1 is strictly greater than x1, but y2 is equal to x2, this case is y greater than equal to x and y not equal to x. Okay, so this is what they mean. Alright, so given two commodities, if for both commodities it is higher, then it is strictly preferred. And strongly monotone means that even if one of the commodities has higher amount, then it is strongly monotone. Okay. Number 2, definition of local non-satiation, or as we know it, more is better. Okay. So the preference relation R on X is locally non-satiated if for all x belongs to capital X and for every epsilon strictly greater than 0 positive, there is y belongs to capital X, that is another bundle basically, another bundle can be found in the same set such that dy d of y minus x, this is basically distance, so the gap between these two is less than epsilon. That means you can go for the nearer than the nearest bundle. Okay, and ypx. Okay. So that means if I change even slightly in any direction, so to say, the vector sense, but let's keep it here. So in even slightly, okay, epsilon is small, we are saying even less than epsilon, even then it will be strictly preferred. So that is called local non-satiation, or more is better. Just a statement which is actually important, that is axiom of local non-satiation is weaker than monotone. Okay. And now a very expected kind of theorem. Let us write it here. So, theorem: if R is monotone, then it is locally non-satiated. So in our structure, some of you may know that in our structure what we take is local non-satiation. We do not go till monotonicity. Okay? Alright. So after the desirability assumptions, the convexity assumptions, those which are going to make our IC convex. Convexity assumptions. So definition of convex preference relation. Again, the preference relation R on X is convex if for all x belongs to capital X, and if y are x and z are x, then so now we are going to make the convex combination alpha y plus 1 minus alpha z. So the convex combination Rx, yes, for any alpha belongs to close 0, 1, right? This condition makes this a convex combination. Okay, now definition of strict convexity. Definition of strict convexity. Okay, again the same start. The preference relation R on X is strictly convex for all x belongs to x if y are x, z are x, and y not equal to z in the same said in the same way okay, that we have said earlier. Y not equal to z implies so the convex combination again 1 alpha y plus 1 minus alpha z. This time it is strict, so px strictly referred to x for any alpha belongs to close 0, 1, so that it does become a convex combination. Alright. Along with that, we have another axiom which just helps our work a lot, the axiom of continuity. Okay, it's a tough work actually to make the IC convex to the origin continuous so that you can just make up a Lagrangian and differentiate and get the demand function. Anyways, so it's pretty simple. The preference relation R on X, right, relation R on X is continuous. Okay. Now, with this setup, we have some extra comments to make here also. Theorem and some notes. Note, rationality is necessary and continuity is sufficient of preference relation R for the existence of a utility function. So if I take the axiom of continuity, it is sufficient. So now definitely we can write the utility function and draw it. Theorem. Suppose that the rational preference relation, R on X is continuous. Then there is a continuous utility function, ux that represents R. Okay. So now we reach a point where we can say that there is a continuous utility function. Okay, so this is the prime reason of having this class, that in a standard UG setup, what happens is everything comes to your board or your book or your pages just like that, which is not true at all. Okay, so behind this is this setup. Okay, it's a little bit difficult, it is mathematical, but it is there whether you like it or not. Okay, note 1. Not all utility functions representing R are continuous. We said it's a sufficient condition, right? any strictly increasing but discontinuous transformation of a continuous utility function also represents R. Okay. So that ends the debate or the misconception regarding need of continuity. All right. Note 2. This is a repetition for those who have seen the class on cardinal Euclid theory, that increasingness and quasi-concavity are ordinal properties of U dot. Okay, so we are going to make obviously a separate video later on this quasi-concavity and quasi-convexity and checking them itself, but that will happen only after we have gone through the optimization exercises. In that way, actually, it is easy to understand them. Okay. So now, the final thing, definition of an indifference curve. So now we can define it. And as I promised, in sense of mathematics and also in sense of a structure which is familiar to economics. So definition of an indifference curve. Right. So let us just check. We are in a two commodity world. That means we have x1, x2. And then we have represented it by x in terms of vector. And then we have got a utility function which is very well behaved. So what we have is actually ux equal to this, right? So that means we are technically in a 3D space. We have three variables, x1, x2 and the utility itself. Okay. Now IC is a 2D idea. You have drawn IC on your copies. That means it's in 2D, right? Otherwise, how can you draw it? So, from 3D to 2D, from a mathematical point of view, we are coming from a 3D to 2D. And it's very simple. Just put a bar here. That is some U bar. Mathematically, it's IC. In terms of economics, we say a lot of other things also. Okay. Let us first see how in maths we should say. So IC is defined as the two-dimensional contour of a 3D utility function. Okay. And in terms of our subject, IC is defined as the locus of commodity bundles among which the consumer is indifferent, that is, derives the same level of utility. Okay. So u of x1 comma x2 equal to u bar. All right. So today in this part we end here. In the next class we will draw the IC, or an IC so to say, following all the axioms, assumptions that we have taken, and from there we will derive all these rules that we have to follow, or the rules that we have regarding the IC, and how all these assumptions and axioms make this IC convex to the origin. And not only that, how convexity is related to the famous law of diminishing MRS. As Mas-Colell puts it, this is the best way of putting it, that if you say that it is convex, it's enough. And if you say that it follows the law of diminishing MRS, that is enough too. So saying one thing means saying the other thing. Alright? So here we end. In the next class, we will start from the diagrams.